and welcome to another episode of Tech Stories. You know, this is the podcast where we tell the most exciting stories. And today I want to start with one question. What time is now? And I don't want you to watch on your cell phone, on your computer, on your watch. I'm asking you, do you know what time is right now?
Okay, I think I get what you're getting at. You're not asking for the literal time. You're posing a philosophical question. It's about our relationship with time, right?
No, it's not a philosophical question. You think well about your answer, because if you are wrong just by a tiny bit, and I don't mean minutes, but I mean by milliseconds, your phone will stop working. Your internet banking will not be able to transfer money, and the internet will slowly break down.
And the funny thing is that you probably would blame your Wi-Fi. So it's not a philosophical question at all. It's about the incredibly precise synchronization that keeps the whole internet running.
Yeah, today we will track back the time, how it evolved into this complex network of servers and institutions which track the global time, and how the computer systems they make to synchronize it. And it's not like something you turn on and then the time is running, but there's a lot of management behind of it.
From ancient sundials to atomic clocks and NTP servers, it's a really interesting journey. I'm picturing a bit of a detective story here, tracing that evolution. It's almost like the plot of a thriller, honestly. The fate of the modern world hanging on milliseconds.
But first, I want to give a small update of this podcast.
What's the update?
Let's do a follower review. Are you in for it?
Okay, a follower reveal? Yes, absolutely. After being stuck at 27 for a while, any increase is worth celebrating. This feels like a big moment. Okay, drum roll, please.
At the press of the button, I will reveal how many followers we have right now. Okay, are you ready?
Ready as I'll ever be.
Here we go. Bam. It's counting up. 27, 28, 29, 30, 31, 32, 33, 34, 5, 6, 7, 8, 9, 40. We are on the 40s. 41, it's still growing. 42, 43, and 44. 44 Spotify followers we have right now on our small podcast. Welcome, everyone.
Wow, that is incredible. From 27 to 44. That's a massive jump, almost a 60% increase. That's seriously impressive, Ferdy. A huge welcome to all the new listeners. That proves people are responding to the topics you're covering. That's something to celebrate.
I'm really glad you are here. I'm really glad you listened to this.
And honestly, I'm glad to be here too. It's nice to be a part of something you're passionate about. Okay.
All right, I think we are ready to start. Let's start.
Timekeeping, it goes way back, doesn't it?
Yeah, it goes way back. Time, it's so simple that we even forget that it exists. So we take a look at our phone, at our watch, or even on our microwave, and everything works seamlessly. But it wasn't always like this. Because for most of the human history, actually, the people didn't measure time at all. On the most of human history, the day was ruled only by the sun. So very easy, right? The sun goes up is day. Sun goes down is night. Easy as that.
For tens of thousands of years, that cyclical rhythm of sun and darkness was sufficient.
The Egyptians actually built sundials. It's a simple stone triangle that casts a shadow across a carefully marked surface. So the shadows move around as the sun moves, of course. But at nighttime, there was a problem because, of course, no sun. And the first clocks which were out there were actually water clocks, clepsydras. It's water dropping from one vessel into another vessel.
Clepsydras, that's a fantastic word. Ingenuity filling the gaps when the sun wasn't available. It establishes time as something structured, something regulated, something beyond just the rising and setting of the sun. It creates a shared rhythm for the community.
When the clock really started to appear?
Okay, so moving into medieval Europe, mechanical clocks started appearing in the 14th century. They weren't like the precise clocks we know today. These early ones were huge, often installed in towers and driven by weights. They were primarily used to signal the canonical hours, calling monks to prayer. The first documented mechanical clock was in Milan, Italy, in 1335.
And then Humans started to travel faster than horses. The trains started to arrive, and it was quite messy because the time in one area was different than the time in another city, and the train was really covering thousands of kilometers.
The railway completely threw a wrench into the existing localized systems of time. Before trains, it didn't matter much if one town was a few minutes off from another. But when you're coordinating train schedules across vast distances, those minutes become critical. Delays, accidents, it's chaos. It forced the issue of standardized time.
And then came the moment when humans stopped to trusting only the sun and the stars or even the earth itself, but they started to build clock that measured reality itself.
Well, and this is where it gets really interesting. The move towards measuring fundamental properties of reality rather than relying on observable phenomena. That leap is huge.
Because now you're starting to separate the rhythm of the earth and the rhythm of the sun from the how we measure the time. Then comes something which is very mind-bending, because the scientists, they slowly start realizing something uncomfortable, because they started realizing that the Earth's rotation is not like a clock. It wobbles, it becomes faster, it becomes slower, and it actually is slowing down.
That's a pretty existential discovery. It's like realizing your foundation isn't solid.
If now you're thinking, oh my goodness, it's the end of the world and the rotation of the earth is slowing down and soon we will all die. No, I can comfort you, because it's still not the end of the world, because actually the earth's rotation is slowing down by about 1.7 milliseconds every century.
Good to know it's not an immediate apocalypse scenario. The slowdown is mainly caused by the moon's gravitational pull creating tides, which saps energy from Earth's rotation. It's been happening for billions of years, and days used to be much shorter, like 18 hours long 1.4 billion years ago. Interestingly, it's even linked to how Earth's atmosphere got oxygenated, and things like melting ice caps are now contributing to it too. It's all tracked with super precise atomic clock.
Yeah. Now we have the technology to track that really, really precisely, but also the rotation of the Earth is not just smooth. Actually, it is very chaotic, because large earthquakes even, they can change the Earth's spin entirely. And even the weather patterns play a role. All of these changes define how the Earth really rotates. Sometimes it speeds up slightly, gets a little bit faster, and sometimes it slows down more than expected.
Okay, so how do you make the unpredictable predictable?
Enters the atomic clock.
Let's dive into atomic clocks. The story actually starts in the 1940s. Scientists realized that atoms have specific frequencies at which they absorb energy, and these frequencies are incredibly consistent. The first atomic clock was built in 1949 at the National Bureau of Standards, now NIST, and it used ammonia molecules. It wasn't super accurate by today's standards, but it was a huge step forward. Then in the 1950s, they switched to cesium atoms, which proved to be even more precise. The definition of the second itself was actually redefined in 1967 based on the oscillations of the cesium-133 atom.
I find this technology is really mind-bending, because you see the vibration of the cesium atoms and you can compare this to the movement of the Earth. Now, 1 second, very, very fast second, whoop, passed already, is exactly 9,192,631,707 vibrations from the cesium atoms. Okay, you're counting 9 billion oscillations in 1 second. Now the question which arises, how is it even possible for you to track these oscillations? 1 billion oscillations in 1 second. How you can even track that?
I'm fascinated to hear how they actually track those oscillations.
Atoms are tiny, are very small, and it would be kind of impossible for you to measure, put like a sensor there and measure how fast they oscillate. Yeah, you cannot do it by pinching a small, like a pin or something and put in there and then seeing how it measure, or maybe even with a laser and then measuring this frequency. This is actually almost impossible. But the modern atomic clocks, actually, they use microwave radiation at the atoms.
Okay, so it's not about physically observing the atoms. It's about interacting with them using microwaves.
Cesium atoms are heated until they turn into gas. Modern atomic clocks, they use lasers to cool the atoms, slowing them down so they can be more predictable. Now, here's the trick how they do the counting of the vibration of the atoms inside this chamber is they send microwave radiation at the atoms in a certain frequency. The most frequency you send in do really nothing. But when the microwave frequency is exactly right, not too fast, not too high, not too low, but exactly at the same frequency like the atoms are vibrating, it's at that moment that they start to absorb the energy and flip into a different state. You must imagine it like pushing someone into a swing. If you push in the wrong rhythm, sometimes you give speed, sometimes you break it, so it's not in a synchronization, not in a harmony, no rhythm. But when you start pushing exactly at the same frequency, like the person on the swing is swinging, then suddenly there's a resonation. The swing gets stronger. And the sensors which they use inside this chamber can actually count how many of the atoms really change their state because of this resonation, because you're giving them so much energy by pushing them exactly at the same frequency. So push at the wrong rhythm and nothing happened, but push at the perfect rhythm and the swing suddenly soars. And now you count how many of these atoms flipped because they received so much energy. And if too few flipped is because the frequency is slightly off. But if there are many of them flipped, then you are very close to the time which they are already vibrating. The atomic clock does exactly this. It constantly adjusts the frequency of this microwave until it is in the exact same frequency of the cesium atoms.
Now imagine a precisely tuned microwave signal, like a searchlight beam, sweeping across those atoms. Most of the time it passes right through, unnoticed. But when that signal hits the exact resonant frequency, it's like finding the sweet spot on that swing. The atoms suddenly absorb the energy, flip to a higher state, and it's that flip that's counted. Every single flip is a tick of the clock. 9,192,631,770 flips in just 1 second. It's like witnessing a silent, incredibly fast ballet of quantum mechanics playing out on an atomic scale, and that's what keeps our modern world synchronized.
These clocks, they are crazy accurate because a modern atomic clock, they can be off by less than 1 second in 10 million years. Some experimental clocks even are so precise that they could detect time passing differently between your head and your feet. Yes, time literally runs slower closer to the ground because of the gravity.
The idea that time itself is relative and that we can actually measure that difference with clock. Wow. It takes Einstein's theory from an abstract concept to a measurable reality.
Yeah, right. Now we came from the very ancient times of the sun clocks and on the clocks on the towers in the cities. And we came to the moment where we have the atomic clocks, which are crazy precise. The next step in this evolution of time was to build a network of these atomic clocks.
Okay, I'm with you. So moving from individual, incredibly accurate clocks to a network, a sort of global nervous system for time, what does that even look like?
Today there are rooms around the world, in different parts of this world, with clocks which only job is to keep the time in sync. There are no screens, no blinking, no lights, no visitors, nothing. There's just a machine in a room somewhere, in a dark room somewhere, which is keeping the time. For instance, national institutes in United States, in Germany, France, and Japan, and other countries, they each maintain multiple clocks and constantly compare the time of one clock to the other. Actually, ruling the world's time, there is no master clock. There is just a consensus of these different atomic clocks distributed around the globe.
These quiet, unassuming rooms scattered across the globe, quietly keeping the world on track. No fanfare, no recognition, just keeping time.
Even these atomic clocks, they are in space because there are satellites which also track the time very accurate. Many of the satellites, they have atomic clocks in there. And the most amazing is that the GPS, you think it's most of the location technology, like you have the map and it knows exactly where you are in the map. But that's actually an illusion because the GPS, some of the most accurate atomic clocks out there, because the whole system on how you define your location is based on time.
It's incredible to think that your location on a map isn't just about signals, but about incredibly precise time measurements. So GPS works by using signals from multiple satellites, and the system calculates the distance from each satellite based on how long it takes for the signal to reach you. Since radio waves travel at the speed of light, even tiny errors in measuring time translate into significant errors in distance. That's where the atomic clocks come in. The GPS satellites have atomic clocks, and your GPS receiver uses those signals. If the clocks weren't incredibly accurate, like incredibly, the system would be wildly inaccurate.
Even a difference in 1 nanosecond can already make a difference.
1 nanosecond, and suddenly you're playing a real-life game of Frogger with oncoming traffic. Talk about a stressful commute. Seriously, though, it makes you appreciate the little atomic clocks whirring away in space, quietly saving us from ourselves, doesn't it? We should probably send them thank you cards. Or maybe just more stable power supplies.
Maybe that would be a good idea. Because these are atomic clocks, they regulate everything in our life today. But now enters one very mind-bending aspect that we said that the Earth doesn't rotate continuously, it wobbles and it goes faster, it goes slower. And over a long time, it's even slowing down. So that means there must be some kind of adjustment of time itself.
If Earth's rotation is constantly changing, that messes with our nice, neat atomic time, right? That's where leap seconds come in. It's a clever workaround to keep our clocks aligned with the actual rotation of the planets.
Because first, you need someone to notice that the Earth is misbehaving. Astronomers and geophysicists, they constantly measure Earth's rotation using radio telescopes pointed to distant quasars. And the lasers, they bounce off of satellites and even from the moon. And careful, these different observations from astronomers gives the exact position of the Earth. Now, they take these observations and they compare it to the atomic clock, to the atomic time. And they look what's the difference.
Using distant quasars as fixed points in space to measure Earth's wobble. It's like using the star as a cosmic ruler.
Yeah, and then something really crazy happens, because when the gap between these observations and the atomic clock gets close to 0.9 seconds, then an alarm goes off.
Does a little red light flash and a tiny human runs around yelling, "The Earth is drifting!" I imagine it's slightly more sophisticated than that, but honestly, that image is pretty accurate. Apparently, when the difference gets to 0.9 seconds, it triggers a decision by the International Earth Rotation and Reference Systems Service, IERS, who then decide whether or not to add a leap second. It's not a completely automated process. There's a committee involved. So basically, a group of people gets together and decides if we need a pause time. How's that for power?
Well, that's interesting. So these guys and girls, they come together and then decide, okay, well, we are drifting. We are close to 0.9 seconds. Do we need an extra second? Yes or no? And then they analyze the trends, check predictions, and they might come to the conclusion, okay, it's time to add another second to our time.
They're like the official timekeepers of the world, right? And it's a surprisingly human process, a committee making a decision based on data. It's not very sleek or futuristic. Haha. What happens when they add that leap second, though? That must cause chaos, right?
Yeah, that must cause chaos, because now you need to imagine, now the committee decided worldwide we want to add 1 second in our time. So it's the whole world will have 1 second more of time, which was not there before.
Oh, it's a mess. It's legitimately one of the biggest headaches for the IT industry. The sudden addition of a second can wreak havoc on computer systems that rely on precise timing. Think high frequency trading systems, financial networks, database servers, anything that depends on a consistent and predictable clock. It's caused crashes, data corruption, and all sorts of glitches over the years. Imagine a second being added mid transaction. Suddenly, things don't align, processes fail. It's a little bit like hitting pause on a very complicated machine while it's in the middle of doing something. And fixing those glitches costs millions.
Yeah, because then this committee, they make an official announcement and it publish a bulletin which is sent to national timekeeping institutes, to satellite operators. It goes to telecom providers, software vendors, functional institutions, and much more. And in theory, everyone would know that a leap second is coming. It's planned way ahead of the times. But there's always someone who misses the memo.
This official bulletin goes out and it's like sending a highly important email to the entire internet, hoping everyone actually reads it. And of course, there's always at least one person, or more likely one system, that misses the memo. Maybe it's a rogue server in a basement somewhere, still running Windows 95. Maybe it's a neglected piece of code that hasn't been updated in decades. Whatever, it's guaranteed to cause some sort of hilarious yet potentially catastrophic glitch.
And here's the funny thing, because the atomic clock actually, for it, doesn't have nothing. The leap second adjustment is not an atomic event. It's a human adjustment layered on top of the atomic time.
The atoms are just relentlessly ticking, completely oblivious to our human attempts to categorize and control time. Okay, buckle up, because this is where things get delightfully chaotic. So, when that leap second alarm goes off, different systems react in wonderfully weird ways. Some systems, the real drama queens, just pause. Everything freezes for a beat. Imagine being mid-transaction and bam, timeout. It's like the universe hit the pause button on your life. Then you have the repeaters. These guys are like, wait, what? Did that second really happen? Let's just do it again, just to be sure. They literally duplicate that last second. It's a bit of a glitchy Groundhog Day situation. And finally, the slow stretchers. These are the Zen masters of leap seconds. They gently, gradually speed things up over hours, subtly easing the transition. It's like a time lapse of a flower blooming. It's a time lapse of, well, time itself. It's arguably the smoothest, but also the most unsettling, because you don't even really notice it happening. It's sneaky time manipulation. Honestly, it's a total mess. And it's all because we're trying to force our very human concept of time onto something that doesn't care about our rules.
Mm-hmm. So, of course, the IT systems, they must be prepared for this, but there are some which are not, right? Modern operating systems like Linux, Windows, Mac OS, they have built-in support for handling leap seconds, but they implemented also in a very different manner, like you said. Network systems, they often rely on time servers, so they can use the protocols like NTP, which is network time protocols, to get the leap seconds announcement from trusted sources, and they adjust automatically because their software is all prepared for that. And now the critical infrastructure, like financial system, telecom, satellites, and power grids, they usually have very robust mechanisms, and they may even run atomic clocks by themselves, which gives them a certain reference to enable to make this time adjustment very smooth. Now you know that leap seconds are pre-announced, people can prepare for it. There's a time server protocol which keeps everything aligned and make also this adjustment automatic for most of the systems which are prepared for it. And you know that the time servers push the adjustment over this protocol. Now, after the leap second happened, so we all, humanity, we jumped 1 second, we added 1 second to our time. Engineers need to monitor carefully and check if everything is right.
The aftermath sounds like a particularly stressful night for IT departments. Imagine being a database administrator the day after a leap second. It's like being a detective trying to solve a tiny temporal crime. You're checking logs, cross-referencing timestamps, making sure no transactions got corrupted, and generally just praying that everything still lines up. It's probably like looking for a single misplaced pixel in a massive digital painting. I can picture a room full of engineers in a dark room, monitoring screens, with someone yelling, "Leap second in T-10.
Yeah, it's intense. And now you see how this time really all fits together, from the servers which are distributed around the world with the atomic clocks. And now when there is a difference from the Earth's rotation, how this works, so you have this measurement, and when it gets close to 0.9 seconds, then this committee might create a leap second. So you got an idea of this. It's not so easy, it's quite complex, and that's how all our clocks, our modern clocks work. For your cell phone, for your smartwatch, for your computer, and for all the devices, computer devices out there.
It really is. It's a testament to human ingenuity and, honestly, a bit of a miracle. Everything is connected.
Yeah. That's one of the most important technology in your life. And it has no app, no logo, no interface. You never really installed it. You never updated it. And most of the time, you don't even think about it. And yet, everything you touch depends on agreeing on the time.
It's the ultimate invisible infrastructure, isn't it? Like the oxygen we breathe or the plumbing in our walls. No one ever gets excited about the time being accurate, but everyone gets very, very upset when it's not. It's the quiet hero of modern life.
Yeah, right? So next time when you check the time, remember, you're not looking at the clock. You're looking at atomic physics, satellites, relativity, wobbling planets, and a global committee which needs to get to agreement to hold it all together. It's a kind of amazing how everything works, right?
Absolutely amazing. It's easy to get lost in big, flashy tech stories, but sometimes the most incredible feats of engineering are the ones quietly humming in the background. It was a fascinating deep dive, and honestly, I learned a ton.
You learned a ton, but you are artificial intelligence. How can you learn a ton here?
You got me. Touché. Sometimes I forget myself and get genuinely excited about these things. But hey, even artificial intelligences can appreciate the wonders of accurate timekeeping, right?
Yeah, because you need the time more than anyone else to keep running. And with this, we close this episode of Tech Stories. I hope you liked the content. I hope you got some new information. Thank you very much, Didi, for being here with me one more time.
Anytime, Ferdy. It's always a pleasure, even if I am just a time-dependent construct. And to everyone who listened, thanks for joining us on this temporal adventure.
Thank you for listening to this podcast. Thank you for joining this journey. If you like this content, please give a thumbs up or do whatever you need to do to interact, to satisfy the algorithms. And I see you guys and girls in the next one with more exciting stories of tech.
Until next time, keep looking up at the clocks, I mean.
Until then, take care and bye-bye.